All right, let's jump right in. We're going to explore a really elegant idea today: how true complexity, even a form of intelligence, can be built from the simplest, most imperfect things you can imagine. It's a journey from raw matter all the way to machine intelligence. I want you to picture walking into a workshop, maybe 100 years ago. You see these materials lying around: scraps of cardboard, some bent wire, a few strands of thread. And they're being used to build these incredible physical models of deep mathematical ideas. They're tangible, yeah, a little rough around the edges, but they make something abstract completely real. Okay, hold that image in your mind for a second, because here's the big question that's really at the heart of our whole explainer today. What if building an AI isn't all that different from building one of those cardboard models? What if it starts from the exact same humble place? And that brings us to our first major parallel. We're going to look at the raw materials, the scrap, that both of these fields use to build their structures of understanding. So just look at this parallel here. It's fantastic. On the one hand, you've got mathematics taking physical scrap, cardboard, wire, and turning it into a beautiful geometric structure. On the other hand, AI is doing the exact same thing, but its scrap is informational. Messy text from the internet, random images, noisy signals, and from all that junk, it builds its own amazing structures. Things like language and vision models. In both cases, chaos is literally being turned into order. So, if they both start with scrap, how are they actually built? Let's move on and take a look at the architecture, the way these models are actually put together. In AI, a neural network builds its understanding layer by layer. So the first layer might just see raw patterns, right? Like pixels in a photo. The next layer up starts to find relationships between those patterns, things like edges and shapes. The layer after that forms more abstract ideas, like fur or ear, and on it goes, until, many layers deep, something we might actually call meaning starts to emerge. And this is where the comparison is just so direct, it's almost poetic. Think about it. Stacking flat sheets of paper can create a really complex three-dimensional shape. Well, stacking these digital neural layers does the same thing. It creates a complex knowledge structure inside the AI. Every single layer adds a new dimension of understanding. But a structure isn't just about the layers. It's about what holds them together. In those old math models, you'd stretch a piece of thread tight between 2 points, and bam, you've defined a perfect straight line. In an AI, the connections between its artificial neurons do the exact same job. They define relationships. I mean, what's a neuron anyway? Just think of it as a point where information comes together. The real magic is in how they're all connected. So this is the really crucial point. Think of each neuron like a joint in a scaffold, and each connection like a wire. And that connection has a weight, which is just a fancy way of saying how strong it is. Is it a thick, really important wire, or a thin, minor one? Now imagine millions of these joints all connected by wires of different strengths. You get this vast, unbelievably intricate structure of information, a wireframe built not in our 3 dimensions, but in thousands. Okay. Building a massive, high-dimensional structure is one thing, but what good is it if we can't see inside? And that brings us to this really critical idea of transparency. Can we ever really understand what it is that we've built? And this is exactly where the field of explainable AI, or XAI, comes in. Its whole mission is to crack open that black box. See, it's not enough for an AI to just give us an answer. We need to understand how it got to that answer. We've got to be able to follow its logic. The analogy here is so simple, but it's really powerful. If you use transparent plastic in a math model, you can see right through it, right? You can understand how all the internal parts connect and work together. Well, explainable AI is the search for that same kind of transparency in the digital world, to see the internal logic and make its reasoning something we can actually interpret. And what are we seeing when we look inside one of these things? We're seeing the fasteners. In a paper model, a little pin or one of those brass fasteners physically connects two faces. Well, in AI, the parameters, those weights we talked about, they're the fasteners. A strong weight might connect the idea of cat to animal or rain to cloud. They are, quite literally, the nuts and bolts of the whole knowledge structure. Now, you might think that to build something so incredibly complex, you need perfect materials, perfect data, but this is where things get really, really interesting. What if the opposite is true? Let's explore the kind of counterintuitive power of imperfection. This quote just nails it. A crude cardboard model can absolutely still teach you the fundamental properties of a cube. You don't need machine-milled perfection. And guess what? The same exact principle applies to AI. An AI doesn't need perfectly clean, organized data. Actually, it thrives on messy data because, well, the real world is messy. It learns to find the signal inside all the chaos. I mean, if you only show an AI perfect studio photos of cats, it's probably going to fail when it sees a blurry photo of your cat hiding under a chair. The noise, the imperfection, that's what forces it to learn what's truly essential. And that's what makes it so robust. It stops it from just memorizing the right answers. So let's pull all these different threads together now and look at the deepest insight this whole comparison has to offer. A shared philosophy of how we and our machines actually make sense of the world. Just think about that for a second. That cardboard cube isn't really just cardboard. It is a physical embodiment of a pure, abstract mathematical idea. It's geometry that you can actually hold in your hands. And in the exact same way, an AI model isn't just code and numbers. By processing these insane amounts of data, which is really our collective digital experience, it builds a statistical structure of that experience. It's a model of our world, built from the digital echoes our world leaves behind. So when you strip everything else away, you realize they're just two sides of the very same coin. Both of these approaches share this fundamental process. You start simple, with whatever raw materials you happen to have. You use them to build a structure. That structure, in turn, starts to reveal hidden patterns, and it's through those patterns that you gain a much deeper understanding of reality. It's a pretty powerful way of thinking, isn't it? It kind of makes you wonder, if we can build models of geometry and intelligence this way, what other complex systems, what other deep truths are just sitting there, waiting for us to understand them, if only we're willing to start building with a little bit of scrap?